Alright, we have a generator here. Here's a generator with transfer, 710 BU1. So we have our service that comes in off the utility. It's in the ground, comes across, feeds the main breaker. Off of here we have a separate panel, separate breaker that comes across, goes to the transfer switch, and it goes to the emergency generator. So here's my emergency panel. Emergency generator comes in, goes across, and goes to the transfer switch. So this transfer switch is what's controlling where the power to that emergency panel goes from. So power's on. When power's on, power comes across, goes to here, comes down the bus bars, goes on the breaker, breaker goes to the transfer switch, then goes across, goes to the panel. So say this is my normal power, this is my emergency, and this is my feeder going to the panel. So if this is my normal power, it's always here. Okay, power goes out, this transfers over, now it transfers over to the generator power, and now my power is going across and feeding the panel off the generator. That's a drawing coming off of Mike Holt's website. So here's the generator going to the panel. Okay, again, you can see these wires look bigger than these little wires going here. So this only has to carry what's in here. This generator only has to provide power for what's in here. I got a little job behind me to size that generator. So again, there may be other breakers in this panel, but power goes off. Whatever's in here is off. Whatever's in there is off. The only thing that's on is whatever's inside the emergency panel. So here's a transfer switch. So here's an automatic transfer switch inside. So I have my input would come into here. Say this is my normal power. This is my emergency power. And then from here it goes over to the emergency panel. And as you can see, it comes off of here, goes down. This is where at these 2 points here, there's breakers. In case I have to turn the power off, I can turn the power off there. But at these 2 points here, this is where the transfer would go. So one may be normally closed, and the other one's normally open. So normally closed, normally open. That's why. Because when normal power's there, this one's always closed, this one's always open. In an emergency situation, it reverses, opens this one, closes this one, now allows my power to come in. So my power to come into here, go across through the transfer switch to the contacts here, and then it comes down and it goes over to these 2 bars. Off these 2 bars, I got one coming up here, and I got the other wire going here. This is a single phase one. And then again, I have my power coming here, goes across, goes through the transfer to the contacts, and it comes right down here. So this one and this one, this one and this one, this one and this one are feeding on these bars. Off these bars, it's going out to here. So from here is where it goes to the emergency panel. My neutrals would be over here. Okay, so again, power comes in off the normal side, off the utility, comes into here, comes into here, goes to here, and then goes to this emergency panel. Power goes out. The sensor senses that voltage went out, current went out. It transfers over, turns the generator on, and this would have a generator start. So it would turn the generator on. Once the generator came up, it would transfer over. The book said it was about 10 seconds. So it would transfer over. Now my emergency power comes into here, brings my voltage to here, it goes to there, and it goes back to the panel. And then this is all done. So this would have the generator start and transfer. It's all automatic. I'll get to that in a bit. Okay, so here's talking about generators. We're not going to talk about the storage batteries. Right now we're going to look at the generators. So the engine type and generator capacity, size larger than required. Size larger than required. Okay, I send you all the sheet on wattage worksheet. So these wattages that I have here, I got them off that worksheet. So in this one, I got a 120/208 3-phase. I have my run and my additional starting currents. Guess what? I have a surge. When the motor turns on, it surges. When we're doing the chapter on motors, we were doing the minimal and the maximum starting torque current according to the code. So you have to look at the letter, find your multiplier, and then that will give you. So we have to allow that. Why? Because the generators get to allow that motor to turn on and run without bogging down. So my lighting is 8,000. There's no extra. AC, got 6,000 watts. Starting 6,700 watts. My fan blower, 1/3 horsepower fan blower, 700 watts running, 1,400 starting. I have a heat pump. My heat pump is 4,700 watts, 4,500 watts starting. But because my AC is bigger than my heat pump, the only thing I need to start is one. I don't have to turn both of them on because I'm not going to be running both of them at the same time. So just like when we were sizing the service, you always have to remember that. Same thing on the generator. Guess what? Find the larger of the two. Find the larger of the two and use the largest. So now I get the AC. So I drop the heat pump. That's why I underline and I got this little X next to it. So we don't use it. Computers. It says the computers have, I have 10 computers. Off the sheet there's 10 computers with 17-inch monitors. They use 800 watts. So I just got the 10 multiplied it by 8. That gave me the 8,000. And then I have a refrigerator. There might be a microwave and a few other things, but those won't run. Only the refrigerator stays on. The other stuff is not non-essential, that they don't have to be running off the generator. Okay, 700 watts. And then starting, it'd be 2,200 watts. So 2,200 watts. So I add these up, and it gives me 23,400. I added these, and it gave me 26,300. Okay, so we shouldn't run the generator at 100% capacity. We should make size it larger than required. Okay, so size it larger than required. So let's say 80% capacity. I want to run it at 80% capacity. So my 88% capacity, I divide it by 80%. It takes me up to 29,250. My surge takes me up to 32,875. Okay, so my running capacity. So now I'm looking at least a 30, maybe a 30 kVA transformer. You know, according to the sheet, I could use something smaller. I went in to do there was a calculator. The calculator said 19. I was looking at one that Mike Holt uses on his on his generator sizing from Generac, and it said that's at 17 kW generator. Calculator said all I needed was a 19 kW generator. So again, you know, for this, I say I can use a 25 very comfortably. I can use a 25 kVA, kV or kW generator. Why? I'm going to use it 23,000 watts. The generator's producing 25. I'm fine. And I'll show you that in a bit. So I turn around and I get my load. This is my load. How many amps is this thing pulling? How many amps is this thing pulling? So I get 23,400 divided by 208. That's my voltage. Times 1.732 three-phase. Okay, if it was single phase, it was a 12240, and it would just be 23,400 divided by 240. We wouldn't do that. So it gives me 65 amps. I go to 31015 B16. The number 6 can handle 65 amps. That's at 100%. At 75 degrees C. At 75 degrees C, you can do 65 amps. So I'm sizing the generator bigger, and then I need to be able, the wire has to be able to carry what the generator's doing. Okay, so my size, you know, maybe I go to number 4 or maybe something bigger, but it's all dependent on the generator. What's the output of the generator? So whatever the output of the generator is, that's the size of the wire that I got to run, not the load that it's carrying. Why? Because people will go in there and plug more things into the generator to, you know, till they get to the capacity, so we have to size it. So this is a thing I found. There was a PDF from Eaton So they're saying the generator standby, so a 20, so 20 kVA, 12208, 30 volts, 80% power factor, and that's what I added over here, that 80%. So it can do 69 amps. Standby is 69 amps. My surge at 30%, it can get up to about 143. Okay, I can go up higher. Here I can go to the 30. At 15, that's not enough. So I can go to the 30 if I want to add more. So it does 104 at 12208. So again, now I got to run a wire that can carry 104 amps. Let me get my sheet real quick here. So 104. I'll be looking at number 2 wire. Okay, so if I was using the 30 and it does 104, standby power is 104 amps. Number 2 wire. Over here I said number 4. So if I'm using over here 20, it says standby amps 69. Well, the number 6 only does 65. So which way you go? Again, because when I did the surge I came up to 29. So if I'm saying I need 29, really can't go by this because this will go at what's there. So you find the amperage, you go to the generators, you can always find it that way. But for right now, if I'm at 29, guess what? I need a 29. I need a 30 kVA. They don't make a 29. They're usually 20, 22, 25, 30, 40, 50. Was reading on this sheet further up, and they were talking about making it larger than what you needed, 25% larger. So let's say if I needed 40,000 watts, then I would use a 50,000 watt generator, a 50 kW generator. So here I need 23, so maybe I want to go up to 25 to a 30. So I'm allowing for future expansion. I'm allowing for future expansion, but according to this, I'll have to size it as the amperage. Don't look at the wattage. Don't get confused and say this, oh, I need a 30. Look at the amperage. You can always come here. Okay, this is the correct way of doing it, is you look at the amperage of the generator. Why? Because generators are going to get that wattage and split it up. So, again, you size it up. That's why I divided by 80% to take me up. So that's where I'm using the 30 kV, a 30 kW generator. That's what I will use, a 30 kW generator. So my wire size, I would need a number 2 because this generator does 104 amps. This generator does 104 amps. 12208, 104 amps. Okay. Again, this is off the sheet. You don't have this sheet. You can find it online and do it. I'm not going to require you. So when you do your assignment, not looking at that sheet, I'm just giving you what the actual thing is. Okay, come in here, I added up. I came up to 65 amps. Okay, this is the way I want you to do it. I came up to 65 amps. Okay, I should load a wire at 100%. Okay, so wire should be able to carry 125. So what's a reciprocal of 125% is 80%. And I divide it. So I got the 65 divided by 80. They gave me 81.25. Now, basically I looked at the sheet. Number 4 can handle 85 amps. Number 4 can handle 85 amps. So I would have either an 80 or a 90 amp breaker. Okay, because the code does allow me to go to the next size up. If it's not on the standard size, I'm allowed to go to the next size up when it's a feeder. Okay, so if a number 4 does 85 amps and I'm at 81.25, guess what? I can go up to that 90 because code allows me on feeders to go to the 90 amp. But I could safely put an 80 amp on there too. Okay, so this is what I want to see you do. Find your sheets. I did a 3-phase because the assignment is a 3-phase. I don't want to get anybody confused. Again, if this was single phase, I'm going to send you a thing on single phase. I would divide that by 240, and I think it's 95 amps. So I'm looking at a 100 amp number 2, or number 3 is with a 100 amp breaker, 110 amp breaker. Okay, add everything up, find your thing, ampacities, then take it up to 125%. So if I'm at 65 amps, my wire size, I want my wire size to carry 125%, 125% of this. How do I get that? I divide my amperage. The amperage is this. Divide it by that 80%, and then that'll give you the amperage for your wire size. Go into the 75 degrees C, because you are talking about a feeder. It doesn't matter if it's 100 amps or less. Look at look at that 75 degree. Pick that, and then that's your wire size. So in the assignment, I'm asking for total load, just like I got here. There's going to be the total load and the surge, wire size, and then generator size. So again, if you come up to here, once you get above 30, they're usually every 10. Okay, so wherever it comes up to, go to the nearest 10. So here I'm at 29,250, so that'll be a 30,000 watt generator, 30 kW generator. All right, good luck and stay safe.